Good morning, dear students. So today we would like to discuss another point. In fact, basically a new concept. New concept means another method of solving some problems, and that method is we can say the center of mass frame. It means some of the problem normally the problem based on two particle system. The problem based on two particle system can be solved by using the center of mass frame. So by this method the problem can be little bit easy. Okay, so first see what is the meaning of center of mass frame. It means when we are looking any object from the center of mass, then what type of scenario we can find. Now see here. That frame, center of mass frame, also called as C frame, center of mass frame, or it is called C frame. Now see, when we are looking from the center of mass itself, so velocity of any of the system with respect to center of mass will be always zero. So momentum of the system will always be zero. So momentum is zero. That's why this frame is also called zero momentum frame or zero momentum frame. Okay, so all these are the same name. So whenever we are saying zero momentum frame, it means we are observing from which point? From the center of mass. See, the first I would like to write the expression of kinetic energy of a system. Let these are the different particles in the system, m1, m2, m3, m4, and their velocity may be your v1, v2, v3, like this. So let m1, m2, mn are the particle in a frame, in a system, and their velocities are v1, v2, v3 respectively. Okay. So kinetic energy of system. So kinetic energy, just I am telling you the expression how to find kinetic energy of system. K is your half m1 v1 square plus half m2 v2 square, like this I can write, or I can say summation of 1 by 2 mi vi square. I value start from here 1 to n, like this we can write. Now the same thing I want to write in terms of the center of mass. So this system will have somewhere center of mass, and this center of mass may have some velocity that we are calling as velocity of center of mass. So this I can write here. See, velocity of the ith particle, velocity of ith particle is equal to velocity of ith particle with respect to center of mass plus velocity of center of mass with respect to ground, or simply we can say Vc. Vc is the velocity of center of mass. So this I can say I can write like this also. So K is equal to your half summation of mi vi. Vi means I can write vic plus vc, and product means vi square means dot product. I can write dot product vic plus vc. Same. Like this I can write. Okay. Now see further. Half 112, I can write here mi. Now simplify this one. VIC square plus VC dot VIC. This is 2 times plus VC square. Like this I can write. Now see further. Half. I am just writing this separately. Sigma mi VIC square 112 plus half sigma mi VC square I is 112 plus this half and half cancel, sigma 112 VC dot VIC into mi. Okay, like this I can write. Further, what is this? This is your summation of kinetic energy of all particles with respect to center of mass, because this is velocity of the ith particle with respect to center of mass. So this is the kinetic energy of the system with respect to center of mass. So K is equal to kinetic energy with respect to center of mass, with respect to COM, plus what is this? Sigma mi is total mass. We see the velocity of center of mass. So this is your half total mass velocity of center of mass. It means it is the kinetic energy of center of mass. And this, see, if I am just doing this one here, sigma. Now little bit changing on this. See, VC dot sigma mi VIC. Now see what is this? M1 V1C. It means this is the velocity of 1 with respect to center of mass, plus M2 V2C. So this whole term will be your total mass. It is just like M1 V1 plus M2 V2 plus M3 V3. And if I am multiplying the total mass into M, so this becomes your velocity of center of mass with respect to center of mass. So this will be your 0. The velocity of center of mass with respect to center of mass will be your 0. So if I am multiplying M total mass dividing M, so this term gives us velocity of C with respect to C. The velocity of center of mass with respect to center of mass, which is equal to your 0. If it is 0, this term will be 0. So kinetic energy of a system, this I can say kinetic energy of the system with respect to center of mass, with respect to center of mass, with respect to COM, and plus this is the kinetic energy of center of mass, half M VC. So in terms of center of mass, kinetic energy of system written as kinetic energy with respect to center of mass plus kinetic energy of center of mass. Now, normally we are solving the problem based on your two-particle system. So I would like to write what is the value of this for two-particle system. For two-particle system, let M1 and M2 are the masses and their velocities are your V1 and V2. So velocity of center of mass will be here. Velocity of center of mass will be here m1 v1 plus m2 v2 by m1 plus m2. Now I am finding kinetic energy of the particle system with respect to center of mass. The kinetic energy with respect to center of mass. So half m1 v1 with respect to c square plus half m2 v2 with respect to c square. Now this further I can write half m1 v1c, v1 minus vc, v1 minus vc, this is called your vc, plus half m2 v2 minus vc. Substitute half, I can take common m1 v1 minus vc value m1 v1 plus m2 v2 by m1 plus m2. Okay. Square plus half this m2 v2 minus vc. Vc value is this. This is the square. Okay. Now I am simplifying it. This is for only for two particle system. Remember, for two particle system. So Hereditism, kinetic energy of system is equal to kinetic energy of the all particle with respect to center of mass plus kinetic energy of center of mass. Now for two particle system, I am finding the kinetic energy with respect to center of mass. See here. So kinetic energy with respect to center of mass. C1 half. See m1 this one, just do the multiplication. m1 v1 cancel. What is left here? m2 v1 m2 v2. m2 you can take common, so you will get your v1 minus v2. So I can write here half m1, m2 I can take common, m2 or see m1 v1 m2 v1, m1 v1 cancel, m2 v1 minus m2 v2. So m2 v1 minus v2 by m1 plus m2 whole square. Okay, then plus see here half m2 m1 v2 m2 v2 cancel, m1 v2, m1 I can take common, v2 minus v1, m2 already there, m1 I can take common, v2 minus v1 by m1 plus m2 whole square. This is coming. See, check it. Okay. Now, kinetic energy with respect to center of mass of a system, half in this here, m1 m2 I can take common, and m1 plus m2 I can take common. So m1 m2 by m1 plus m2 I can take common, and v1 minus v2 square and v2 minus v1 square. both are same. So V1 minus V2 square same. Now what is left here? M1 and 1 M2 I took common. 1 M2 left over and M1 plus M2 left over. M2 by M1 plus M2. Here, in this M1 M2 I took common. M2 I took common, M1 left over here. M1 by M1 plus M2. Now we can simplify this become your 1. So kinetic energy with respect to center of mass written as half m1 m2 by m1 plus m2, and this is your v1 minus v2 square. This term for two particle system, it is called reduced mass. It is called reduced mass. Mu is equal to your m1 m2 by m1 plus m2. And see this term v1 minus v2. v1 minus v2. It is nothing your relative velocity of the particles. V relative. So I can say kinetic energy of a system with respect to center of mass written as half mu V relative square. This is very important result which we are going to use in the coming questions. Okay. So in fact this is the relation. This is your mu reduced mass and this is your V relative. This relation we have to remember. What is this? This is the kinetic energy of a system of particles with respect to center of mass. For how many particles? Two particle system. So which is equal to your 1 by 2 mu V relative whole square. Now note down this. Now see the use of this, application of that. Very important here, application. Okay, see. Note down this. Okay, fine. Now see the one of the application of this. So this is a different formula. This is kinetic energy of system in terms of your kinetic energy of center of mass and kinetic energy of all particles with respect to center of mass. Now see the application of this. Okay, see. See the example of this, use of this. Let these are the two particles of mass m and 2m. Okay, this is let given a velocity here. We can say that your v naught, and this is given a velocity also your v naught. Find the, now I can write like this, two particles each of mass, two particles having mass m and 2m, two particles having mass m and 2m are connected with an ideal spring of force constant K. Constant K. Yes. Okay. Connected with an ideal spring of force constant K and kept on a smooth horizontal surface. Both the particles are given velocity v naught opposite to each other. Both of them given velocity v naught opposite to each other. Opposite to each other. Okay. Find the maximum elongation in the spring during their subsequent motion. During their subsequent motion. Subsequent motion. Okay. See how to solve. So if we are solving by center of mass theorem, there are two methods of solving. One by using center of mass theorem without, and another is without using center of mass. First, from method 1. Method 1, from center of mass, from C frame. C frame means center of mass. If we are looking from center of mass frame, the system will have how much kinetic energy with respect to center of mass? 1 by 2 mu v relative square. And if this is moving away from each other, so as we know, this frame is called your center of mass frame. The center of mass frame means momentum of this will be your, momentum from this frame will be your 0, always 0. The momentum from this frame will be always 0. So there are two things are there. There are two things are there. During the subsequent motion, velocity of these two particles will change, because as the force, as they are moving in this direction, so this spring force will act. Because of the spring force, this velocity of both the masses will change continuously. But that change will be always in such a manner. Momentum of the system with respect to center of mass will always 0. So as the velocity of this wave continuously decreasing, so one instant may come when their velocity become 0. At that time also, so center of mass velocity will be also become 0. At that time, the elongation of the spring will be your maximum. It means all of the kinetic energy of the system, okay, with respect to center of mass convert into spring potential energy. So directly I can write here the initial, this is the initial. The kinetic energy of the system with respect to center of mass is equal to half K x maximum square. It is. Now how much is this value? Half. Same formula. Mu. Mu is m1 m2 by m1 plus m2. m1 m2. M into 2. 2m square. 2m square by 3m. m1 plus m2. v1 minus v2. Relative velocity. Relative velocity, this is v0, this is v0. So relative velocity of 2v0. 2v0 is equal to half k x maximum square. Now you can simplify. This half cancel. 1m cancel. So 4v0 square. 4 into 2, 8. 8m v0 square by 3 is equal to k x maximum square. X maximum is equal to root over 8m v0 square by 3k. This is your answer. This is better one from C frame you have observed. But if you are observing from the ground frame, then what? How to solve? See. From another frame. Now method 2. From ground frame, that we can say. Ground frame is normal method. Okay, normal. See, 1 minute. Now, if you will analyze from the ground frame, then see what will happen. Because of the velocity here, both start moving away from each other. So, spring will have some elongation. Spring will apply force on both of them. See, from ground frame. Let this is the initial position. Mass 2m, mass m. Right now this has been given velocity v0, this has been given velocity v0. Fine? Okay? And spring has a spring constant here. This is your initial. Initial spring is like given here. As these two have given velocity v0, let this is the initial position of this. This is the initial position of this. Okay? As they are moving, so after some time this may have somewhere here. This may have somewhere here. Let this displacement your x2. Now the velocity of this will change, let v2. And this will have somewhere here. This the speed your x1 and velocity of this will be your v1. So how much elongation in the spring? x1 plus x2. So elongation in the spring your x is equal to your x1 plus x2. It means spring is applying force here how much? Kx this, kx this. See, important point. Force on both the block is same, and that force is opposite to velocity. That force is decreasing the velocity, but mass of this is 2m. So retardation of this is kx by 2m, and mass of this is m. Retardation of this is m by kx by m. So this block will have more retardation as compared to this. So this block will come to rest first initially here. This is your first question. This block will come to rest. Suppose somewhere here, its velocity of this becomes 0. But this block is still moving. Still moving in this direction. Okay. This block is still moving in this direction. But now if I am talking about force, so force here is kx, here force kx. Now this start moving in this direction. But this velocity slowly decreases. So since this velocity of v naught, now this velocity increases. And this velocity decreases. But still, gap between these two is still increasing. Why? Because v2 initially is more than the velocity of this. One stage will come when both will have same velocity, v and v. Both will have same velocity, but the forces on this is kx, this is kx. When both will have same velocity, then the elongation will be a maximum. Same velocity or it is the same speed in the same direction. Then they will have maximum elongation. Why? Because after that, because of the velocity and force both in the same direction, this velocity will increase and this velocity further decreases. So now the gap between these two will start decreasing. So what we can say, the moment when relative velocity between the blocks is your 0. When the relative velocity, see the relative velocity v and v. When the relative velocity between the block is 0, at that moment spring will have maximum elongation. So when relative velocity between the blocks are 0, relative velocity between the blocks are 0, then the elongation in the spring will be maximum. Elongation in the spring will be maximum. Now how to solve this? So now in the system only kx force acting in the horizontal direction, and this kx is equal and opposite. The net force in the system is 0. Net force in the system is 0. So conserving momentum in the by conservation of momentum from conservation of momentum. So P initial equal to P final. Initial means initial time, starting time here. Right side I will take positive and left side negative. Initial momentum 2m into v naught of this block and this side minus mv naught. And final, this both are same direction. So 2 mv plus mv. So from here you will get v is equal to your v naught by 3. It means that at the time of maximum elongation, velocity of both block is your v naught by 3. Next thing we can write here by conservation of energy. See, since only spring force is there, that is a conservative force, so mechanical energy of system is constant. Mechanical energy is constant. Initial mechanical energy, initial spring elongation was 0, so no potential energy. So initial kinetic energy of this plus this, so half mv naught square plus half 2m into v naught square. Kinetic energy. Final kinetic energy, both having the same velocity. Mass is 2m plus m, 3m. So half 3m v square. V is your v naught by 3 plus spring compression, spring height elongation, that is maximum, half k. Now simplify, check it. On simplifying, 1 by 2, 1 by 2, 1 by 2, 1 by 2 cancel. mv naught square you can take common. 1 plus 2, and from here minus 3. 3 by 1 by 9 minus 1 by 3. K x maximum square. 2 plus 3 is 9, 8 by 3. So from here you will get x maximum is equal to your 8 by 8 mv naught square by 3k root over. See this and this. Check. Both are same answer. Understood? So this is with respect to ground frame and this is with respect to your C frame. So I think you have found this is only one line step, and here you have to analyze. So what you have to do, when the relative velocity between the blocks are 0, then the elongation in the spring will be maximum. So first you have to conserve momentum, and second you have to conserve mechanical energy. So there are two different methods of solving the problem. See another example. Okay, now see another example. Okay, see what another example. Okay, here two blocks of mass m and 2m are connected with an ideal spring and kept on frictionless surface. Block of mass 2m given a force, constant force F. Block of mass 2m given constant force F as shown in diagram. As shown in diagram. Find the maximum elongation in the string. Elongation in the string. Okay, how to solve this? Here in place of velocity, here force is given. So center of mass will have acceleration. So first we will find, so there are two methods again here also. Method 1. From C frame. C frame is center of mass frame. Acceleration of center of mass. M1 this total force by mass. Total force here F by mass. M plus 2m. F by 3m. Okay, F by 3m. Now I am making a video of this. A video of this. This is your center of mass. This is ACM. 2m mass, m mass. A video of this. So see here. As we know, with respect to center of mass, momentum of the system will be always 0. So here forces. One force here, applied force F. Center of mass here, with respect to center of mass, I am making a PD with respect to center of mass, pseudo force. Pseudo force here in this direction. How much pseudo force here? 2m into SCM. Here pseudo force m into ACM. Now, so these are the work done and the spring force. One another here I can say the spring force. At any time Kx. Okay. So work done by all forces is equal to your change in kinetic energy. Now with respect to center of mass, since momentum of the system is 0, and as we have found, initial momentum, initial velocity of these are 0. So when they are at the extreme position, then also their velocity should be 0. Then only the momentum will be 0. So by work energy theorem, by work energy theorem, work done by all forces, delta K, which is delta K is 0, work done by all forces. See here, work done by all forces. This was earlier here, it has been displaced by x2. This has been displaced by your now. This has been displaced here in that side, that x1. So work done by all forces, F minus 2m ACM into x2. Okay, and here work done MACM into x1, MACM into x1. This is the work done by all forces, and this is equal to minus work done by spring. The spring, your force always opposite to displacement is kx, x2 here, displacement here, kx is that side, minus half k, in fact this is x max square, which is equal to your 0. Now substitute the value of, and here x is nothing, x1 plus x2 because they are moving away. So one equation, and x is equal to your x1 plus x2 x max. Now simplify, check it. F minus 2m ACM, 2m ACM, m ACM is f by 3, 2f by 3 x2 plus m ACM f by 3 x1 minus half k 0 f by 3 x2 f by 3 x1 f by 3 x1 plus x2 half k x max square. So x1 plus x2 is equal to x max. So x maximum is equal to your 2f by 3k. This is the answer. So maximum elongation in the spring will be your 2f by 3k. This is the one method. This is called your from C frame. From ground frame. Method 2. From ground frame. Now if we are looking at the ground frame, same concept here. In the ground frame forces, earlier this was here, now this block is here. F is the force and the displacement of the block is your x2, and this block is here, displacement of the block here x1, and here this here 1 minute. Since in this block only kx force is there, so this block was in fact earlier here. Earlier it was here, now the block is here. So this is the displacement here x1. So kx here, m mass, and this is your x2. So first of all x, kx here. See the equation for x. X is the elongation in the spring. This is moving in this side, this is moving in this side. So elongation is x must be equal to your x2 minus x1. This is moving more, this is moving less. Equation for this, f minus kx 2m d2 x2 by dt square. For this, kx is equal to m d2 x1 by dt square. Now see from the second end. So from here see d2 x2 by dt square minus d2 x1 by dt square. This is equal to your d2x by dt square. Differentiate this, then I kept it. Substitute the value from here, this here. F minus kx by 2m minus of kx by m Okay, see this order. F by 2m minus k 1 by 2m plus 1 by m x. X is what is x? X is the in fact relative speed here. So I can write here d by dt of dx by dt. Dx by dt is nothing, it is the relative velocity. dv relative by dt. Like this I can write. Now I can simplify 3m by 2m 3 by 2m into x. Okay, further this term can be written like this. dv relative by dt can be written as b relative dv relative by dx, which is equal to your f by 2m minus 3 by 2m into x. Now, as we told you in the last example, when the relative velocity is your 0, at that time the elongation will be your maximum. So we write here dv relative integrate, and this relative velocity is 0 to 0, f by 2m minus 3 by 2m into x dx. Limit of this 0 to x maximum. Okay, then simplify this and you will get answer, same answer you will get as we have found this one. 2m you can remove, 2m will go their side. This is your x square by 2, the 2f by 3. That gives us x maximum is equal to your 2f by 3k, the same answer as you have found here. So there are two methods here, one by using C frame, center of mass frame, and another method is your ground frame. Ground frame method is your very practical, and you can see, you can analyze the situation, and C frame method might be a little bit easy, but this is your sort of more conceptual method. Okay, so thank you, thanks a lot. Tomorrow I will continue with this variable mass system.